I'm Leslie Goldberg, and I'm a professor of computer science, and I'm going to be telling you about a subject called computational complexity. And officially it's down as 20 minutes and then 10 for questions, but the truth is that in my area, it's normal to interrupt with questions, and I'm perfectly happy to have questions at any point. And actually that's better, because if you think of a question and then you wait, then you may forget, and it may be that I forgot to say something. So feel free to interrupt me at any point. The purpose of the talk is to tell you a little bit about the research field, what it is, and primarily what it's for. Yeah? Okay, so we'll do that. Okay, so first the dry stuff. So computational complexity it's about classifying computational problems according to how difficult they are. That sounds a little boring, but the truth is that problems actually have an inherent difficulty, which captures really how hard they are. And I'll tell you what I mean by that, but I'm going to do it by starting with an example. So this is an example that maybe takes you back, well, depending on your field, to something that you saw in school. You probably saw in school, or maybe some of you are experts that know more about it than I am, who knows, but anyway, prime numbers. So I'm going to talk about the problem of working out whether a number is prime or not. So if you haven't seen it for a while, a number is prime if you look at all the smaller integers, or I think they're called whole numbers in schools. If you look at the smaller ones, the only one that divides into it is 1. Okay, so 5 is prime because 2, 3, and 4 don't divide into it. 9's not prime because 3 times 3 is 9. Okay? And I put this example down just to illustrate why this is a computational problem. This happens to be prime, but of course I use a computer to figure out the example to put on the slide, because there's no way to see that just by staring at it. Okay. So the problem that I want to consider is the problem given a number. How can you tell whether it's prime or not? Now, what we're interested in is algorithms, and algorithms, they've suddenly become fashionable in the media, but they're nothing new. They go all the way back to Euclid, really even earlier. An algorithm is just a step-by-step method for solving a problem. So what I'm going to do, I'm going to start by considering the algorithm that you would probably invent. If I asked you to solve the primality problem, it's at least what I would do. Maybe you'd have some other more clever thing. But let's start with the simplest possible algorithm. If you want to work out whether a number is prime, you need to know whether any of the smaller numbers divide into it. So what you could do, you could check. Yeah? Check them all. So that's a simple algorithm. And what I'm going to tell you is this algorithm's just not feasible. And in order to tell you that it's not feasible, I'm going to start out with something that looks like who cares, and then I'm going to tell you why you might care. Okay? So if we have a number with n digits, and you just checked all the smaller numbers to see whether they divided in, you'd have to check about 10 to the n minus 1. Don't worry about the details, but there's 10 digits, there's n minus 1 places. So there's 10 to the n minus 1 smaller numbers to check, okay? So that's how many. And the next slide is going to give you some idea why you should care about that, okay? So we're going to take it slowly, and what we're going to do is we're going to say, suppose that you have a pretty fast computer. So suppose it only takes you a microsecond to check one smaller number and see if it divides in. Then, if you had to check 10 to the n minus 1 of them, if you had to look at a 20-digit number, the amount of time it would take is about 3,000 centuries. And 30-digit number, 40, I mean, the point is, yeah, you're not going to run it, are you? I mean, that's not going to happen, okay? Now, an interesting thing, what I've also put on this slide is, what if by some cleverness or magic, what if you'd invented a smarter algorithm? And what if you'd invented an algorithm that when it looked at an n-digit number, you only had to check n smaller numbers, not 10 to the n minus 1, but n. Then you could see from this picture that as you got 20, 30, 40, 50, 60-digit numbers, it's a puny fraction of a second. Very, very fast. Okay, so very fast, very slow. And the next thing I want you to take from this slide is that actually there's a qualitative difference. And what happens is, if the number of smaller numbers that you have to check is a polynomial, which is just like n to the something, n to the 1, n to the 2, n to the 5, if you look, it's feasible. Yeah, it might take minutes. You have to get a coffee if you're trying to do a 60-digit number, but it's not something you can't do. Yeah? But if the amount of numbers to check is exponential, by which I mean 2 to the n, 3 to the n, 10 to the n, well, you quickly get into the century zone. Okay, so there's something qualitative important that happens between that. And so tractable problems are ones which can be solved in some polynomial number of time, so n to the something. And you can see from the table why that's important. Now, I was a little bit, I snuck it up on the top of the slide. When I first told you about this problem, I called it a tractable problem. So I told you it was one you can solve. But then I looked at the natural algorithm and I showed you how horrible it is. It takes centuries, okay? Now the truth is, this problem is not inherently difficult. The first algorithm we all think of takes exponentially long. It takes centuries. Actually, every algorithm that we knew until 2002 took exponentially long. But there exists a very fast algorithm for this problem. It's just we didn't know about it until 2002. So in 2002, Agrawal and a couple of other people in India found a polynomial time algorithm. So they studied this problem, and they showed that although the dumb algorithms sit down here, there's actually a way to do it up here. So that's an easy problem. We didn't know, but it's an easy problem. Okay, now, what do we want to do in complexity theory? We want to know which problems are easy and which ones are hard, right? We want to know the difference between a problem that might be easy, but we just don't know how to do it yet, and ones that actually we can prove no matter what happens, they live down here. So next, let me tell you about that. So I'm going to give you an example of a problem that has no good algorithm. And there are lots of important examples, but I chose a whimsical one because I don't have to define anything, okay? So this is a picture of the game of drafts, which I think board games are maybe less popular than they once were, but have you seen this game before? Okay. Yeah, if you haven't seen it, it doesn't actually really matter. It's a game that's played on an 8x8 board, and it's got pieces, white pieces and black pieces, and there are some things you can do. You can move them forward and jump, and you can move diagonally if you jump, and you want to wipe out the other guy's pieces. It doesn't matter the details. But the problem I want to consider is playing drafts. If you were playing drafts, and here I have to talk about the n by n board because it doesn't make sense to talk about the difficulty of a problem of a fixed size, right? We're interested in how it grows. So we'll talk about playing drafts on an n by n board, and the question is, I give you a configuration of the pieces, not that one, and I say, can white now force a win? So if you play perfectly, can you force a win from this configuration? Now the interesting thing about this problem is this is provably different. So it was known since 1984 that there is no fast algorithm. It doesn't matter how smart we are in the future, one will never be developed. It just doesn't exist, and we can prove it. Okay? No such thing. Any algorithm for drafts, no matter how clever, no matter what ideas people come up with in the future, it will always live down here because that's a provable fact. Primality, it was the best we knew, but it lives up here. Okay, so what we'd like to do is we'd like to know the difference. Now, next question is why? Why do we want to know which problems are easy and which are hard? Well, one thing that you might not have thought about is that both are really useful. So it's kind of obvious that if you can solve a problem quickly, that's useful because you can solve it. But it's also very useful if you can't solve it quickly. So if we can prove that a problem's difficult, that's wonderful because all our crypto systems are based exactly on that. Like when you send a message on the computer and it's encrypted, you want people not to be able to read it, that's always based on the fact there are problems that we think cannot be solved. So in fact, a lot of crypto systems that are used in practice are based on our belief that factoring is difficult. So I've just told you it's easy to tell whether a number is prime or not, but we still don't know whether we can quickly break it into its prime factors. If you could, you'd be breaking RSA and a lot of crypto systems that are actually in use on your computer. So that's an unknown thing. So we want to understand. Now, it's quite difficult to classify all problems, and there are some reasons why we don't ultimately hope to. It's a vain hope to understand the difficulty of all problems because there are provably infinite hierarchies and all sorts of complicated stuff. And so what we normally do is we focus on broad classes of problems where there is a hope of kind of doing some classification and understanding what's going on. And what I want to do next is tell you about perhaps the most famous open problem in computer science, which involves a class of problems that we cannot yet classify. But you'll see it's kind of bizarre that we don't know something so simple, but indeed we don't. Okay, so let me start with an example. Okay, so you own a big company, and you've got a list of N employees that work for your company, okay? And what you need to do is you want to assign M of them to a project. Okay, so that's what you want to do. But your company is huge, and you've got a list of pairs of people who cannot be together. So Smith and Jones hate each other, don't choose both of them. Okay, you got a bunch of pairs like that. That's what you're faced with. And the question is, are you doomed, or is there a set of M employees that you can actually choose that obeys all the constraints? Okay, now this problem, if you take some reasonable numbers, like I chose here, N is 400 and N is 100, I just chose this because they're nice round numbers. For these particular numbers, the number of possible solutions is bigger than the number of atoms in the known universe. Okay, so you're not going to just try every possibility and see if it's okay, because that's ridiculous, okay? But this sounds a lot like our original stab at primality, right? We said, oh, we'll just test every number, whoops, there's too many, and there was a smarter way. So the question here, is there a smarter way? Okay, so is this problem inherently hard, so you just can't do it, or is there some clever way that is just more clever than looking at all the possibilities? Now, I've called this a problem which is easy to check. And what I mean by easy to check is that if I handed you a solution, you could tell whether it was good or not, right? If I chose M people out of the N, and I said, here they are, they're all good, and you had the list of incompatibilities, it would be a trivial task to just go through it and check, yep, absolutely fine. So this is an example of a problem where checking a solution is easy, but finding a solution, we don't know whether it's easy or hard. Okay, now it turns out that this frivolous example is actually a famous mathematical problem. And to tell you about the problem, it's called the P versus NP problem, and I'm not going to really tell you what that means. I'm just going to... so this is a problem which is does there exist a problem where it's easy to check the answer, but you can't find it? Now, the bizarre thing is, we don't know. For all we know, every single problem where you can check the answer, there's some magic way to find it, and we just don't know it yet. That's the state of knowledge. That's the ridiculous state of knowledge. So this is a famous problem. And in fact, I've not just shown you an example of the problem, I've shown you the whole thing. If you could answer this silly little problem about companies and employees, you would have solved the whole thing. Okay, so and that's because we actually know that if you could solve this problem quickly, if there were a fast algorithm that would solve this problem, then every single problem that's easy to check, we could actually check quickly. We would know how. Okay, so all the hardness lies right here. At the same time, if you could prove that just like the game of drafts, there's no fast algorithm for this, you would have proved there is a problem that's different. Okay, so the Clay Institute is a mathematics institute which has recently moved to Oxford, actually, 2 years ago. They've moved to the Maths Institute at Oxford. And something that you may have heard about, if you're old like me, is that back in year 2000, they introduced some famous problems. And you can see here on the right-hand side a list of big open mathematical problems. And so these were the Millennium Problems, and there was a prize of $1 million for solving any of them. And the problem I've just told you about, the P versus NP problem, is one of them. Okay, so there's a big prize for solving this problem. Of course, we don't know the answer. I just add as an aside that actually one of the problems on this list has been solved since then. It's by a guy called Perlman. You might have heard about him. He was a kind of eccentric mathematician in Russia, and he's turned down the prize money. But anyway, that's the situation. The rest of them are all still open. Okay, but that's the P versus NP problem. Okay, now, the next thing I wanted to tell you is that it would be wonderful to solve the P versus NP problem, but that's a very ambitious thing because, this is one of the major open problems in mathematics. And what most of us do instead is we try to solve the problem in smaller domains where there's a hope of understanding, right? So identify smaller domains where there's a hope of actually understanding where the boundaries lie between things you can do and things you can't do. And so I thought I'd give you an example of the sort of problems which are actively being studied and which were actively being classified. Okay, so I'm going to start out by just illustrating a little example that comes from statistical physics, purely to show you the sort of computational problems that are kind of on this boundary where we really have a hope of understanding the truth. Okay, so there's a model called the hardcore lattice gas model, and I apologize to any physicists in the room because there's going to be no physics in my explanation at all, but I'm just going to tell you in a sort of mathematical way what the model actually is. So basically you've got some kind of an underlying graph. A graph is just a collection of nodes connected by lines which are edges, and obviously it'll be bigger than that one, possibly it's even infinite, but we're just looking at this picture to give us an idea. And the model is a model of a gas. And so the idea is that at each of these points, these nodes, they can either be occupied, and I've colored them blue, or they can be unoccupied, and I've not colored them blue. And the idea is that these particles have mass, so you can't have occupied next to occupied, because there's not enough space. Okay, and so what they're, so this is a model. And typically a configuration is just an arrangement in the model. So here I've shown you one with 3 blues and the rest white. And this typically there's a weight in the model. So the weight of this configuration, there's a parameter lambda, which says how much it's usually about an external field on the model. It doesn't really matter. Anyway, it's a weight lambda. And the weight of this configuration is lambda cubed because I've got 3 that are colored blue. Okay, now, the problem that physicists are interested in, 2 problems. One is sampling a configuration with probability proportional to this weight. Now, the reason they want to do that is because that tells you something qualitatively about what a typical configuration would look like. Okay, so that's what that's for. You also want to compute the sum of the weights. Like, summed over all configurations, sum them up with a weight proportional to their weight. The reason for that is that's the kind of normalizer in the probability distribution. Okay, now it turns out that this is a problem that we understand everything about, and actually only very recently. In the last probably decade, there's been lots of research on the difficulty of this problem. And what happens is, I've only shown you a little piece of the graph, but you can see that, for example, this node here has 4 neighbors, and nobody has more than 4 neighbors. And it turns out there's a complicated formula that trades the difference between lambda, how big the parameter can be, and the number of neighbors of nodes. And depending on that trade-off, the problem is either easy, so it's polynomial time, tractable, or it's NP hard, which means that it's as hard as all those impossible problems like the employee one. Okay, now I just want to say one more thing about this, which is that you can represent this whole model with a cute little picture. And what this little picture on the right means is that we have unoccupied or occupied. Unoccupied can be next to unoccupied, and it can be next to occupied, but there's no loop here because occupied can't be next to occupied. This isn't deep, but it's because of something on the next slide that I'm telling you this. Is it clear what the little picture means? Okay, and there's a lot of work then, so there are many particle models, not just with two types, occupied, unoccupied, but with lots of different types, and a lot of work goes into classifying the different models, and so I'm going to close the formal part of the talk by just showing you a picture. So forget the colors for a minute. This is a picture of a lot of models of particle interactions that you could have, where there are three types, type 1, type 2, type 3. So this model here says that type 1 can be next to type 1 or type 2, but it can't be next to type 3. Type 3 can only be next to type 2. Type 2 can be next to anything. So this is a model. And what the color scheme is that in fact all of these models have been classified. So the green ones are ones for which the computational difficulty is easy, polynomial time. The blue ones, the computational difficulty is an intermediate thing. And the red ones, the computational difficulty is as hard as the employee problem provably. Okay, so that's just a little picture to show.